Hello everyone, my name is Nun Fatia Jana Pitri Johan, number metric 88251204. Today I will be talking over to guide you through our engineering project overview, final recommendation, and the ultimate conclusion of our study. As we look at this overview slide, our team was tasked with auditing two highly dynamic civil engineering cases. On the left, Case A focused on smart city development. Here, we apply first order ODE to model rapid urbanization and project the total municipal water demand for the Green Horizon smart city development all the way through the year 2040. On the right, Case B addressed a critical on-site structural safety issue. We analyzed the thermal cooling rate of a massive concrete bridge pier during hydration at the Jambatan Putra Perdana project. Our main engineering goal here was to find the exact timeline to safely remove formwork panels and prevent catastrophic thermal shock.
Moving on to the methodology, for case A, we are looking at the population growth model. We start with the basic differential equation dP over dt equals Kp. To solve this, we use 6 simple steps. Step 1, we separate the variable. Step 2, we integrate both sides. Step 3, we apply exponential e to both sides to clear the natural log. Step 4, we simplify by letting the constant e to the power of c equal a. Step 5, we apply our initial condition where at time t equals 0. Step 6, finally, we substitute a back into the formula to get our final population model. So, for the next case, which is case B, we look at the temperature model using Newton's laws of cooling. Our stating differential equation here is dt over dt equal negative k time open bracket t minus ts close bracket. We follow the exact same 6 steps to solve it. Step 1, we separate the variable to get 1 over t minus ds dt equals negative k dt. Step 2, integrate both sides to get natural log. Step 3, apply e to both sides to clear the log. Step 4, just like before, we let constant e to the power of c equal a. And apply initial condition at t equals 0 for step 5. And for step 6, we substitute a back in to get to our final temperature model. And that's all for the methodology.
Hi, Assalamualaikum. My name is Nur Batisha binti Nur Azam. My matrix number is AA250257, and today we are from Group 5 wants to presenting about manual calculation for case A and case B. So, when planning a new building project, we have to look at both the long-term infrastructure impact and the immediate hands-on construction physics. Today, I walk you through our manual calculation for two critical design components. For case A, where we forecast future water demand for the community, and case B, where we calculate the precise thermal safety limit for pouring concrete. So, for case A, is population growth and water demand. So, So for the step 1, we need to know how fast the area is growing. Using our baseline population of 3,000 PO and a 5-year population of 40,000, we apply an exponential growth model. Solving for our growth constant, K give us 0.057536 per year. This is the mathematical heartbeat of our population expansion. Next, for step 2, we fast forward 14 years to the year of 2040 by plugging our growth constant back into the formula where t equals to 14. We project that the population will hit approximately 67,136 people. Notice that we round this to the nearest whole integer because you can have a fraction of a person. And lastly, for step 3 is for daily water demand. Now for the engineering application, assuming a standard water consumption rate of 150 liters per person per day, we multiply this by our 2040 population To make it a manageable utility metric, we divide by 1 million to convert it to megaliters. The final result, the local water infrastructure need to supply 10.07 megaliters per day by 2040. Okay, we move on for case B, which is concrete temperature and setting clock. For step 1, we need to determine the cooling constant, which is K. So, we shift our focus to concrete pouring mechanism using Newton's law of cooling. Concrete generates a lot of internal heat when mixed. Here, we observe that it starts at 70 Celsius for T0 and drop to 60 Celsius after 2 hours. Solving the differential equation yields a cooling constant of 0.139794 per hour. For step 2, we have time to reach the safety limit, which is 35 Celsius. So why does this matter? Because concretes become structurally compromised or difficult to handle if it cools past a safe threshold. We want to find exactly how long it takes to reach a safe limit of 35 Celsius. Rearranging the formula and solving for T, we get roughly 13.75 hours of functional window. And step 3, we converting to clock time. As engineers, we can just tell a site manager, you have 13.747 hours. We need a real clock time. We break down the decimal, 13 hours is clear. And 0.7468 of an hour equates to roughly 45 minutes. If our concrete pour initiate exactly at 8 a.m., adding 13 hours and 45 minutes means our absolute deadline to finish operation safely is 9:45 p.m. that same evening. So that's all for me. Thank you.
Hi and Assalamualaikum. My name is Nur Anisa Imani binti Mama Amran. My matrix number is A82500088. Before we run the digital simulation, we had performed manual calculation based on theory method to ensure using a right method. Based on case A, which is urban growth, we can observe a consistent and rapid upward trend in population growth starting from in the year 2026. By our target, which is 2040, the population reached its peak requiring a massive volume of water. This simulation data can help engineers to properly plan the capacity of water treatment plants to ensure the long-term stability. Now, we move on to the next case, which is a thermal safety. At the very beginning, the concrete is at maximum peak temperature, which is 180 Celsius, which is under unsafe status. If the concrete cools down too rapidly or unevenly, it will crack due to thermal shock. We can see the temperature drop sharply within at the first 5 hours and gradually stabilize after 20 to 25 hours. This simulation analysis helps engineers to determine the safe exact time before removing the formwork.
So, moving on to our engineering actionable item, this slide outlines the final recommendation derived strictly from our mathematical calculation and digital simulation. We have broken this down into three core dimensions: infrastructure, operation, and safety. First, for infrastructure, to safely handle the rapid urban expansion and peak hourly loads by the year 2040, we recommend the City Council design the new water treatment plant with a minimum capacity of 10.5 mld. This guarantees supply integrity. Second, for operation. For the Jambatan Putra Perdana Barrage Pier, the data prove that stripping the formwork panel during day shift is highly dangerous. Operation must be strictly prohibited during the day and should only start after 9:45 p.m. once the core temperature drops safely below the threshold. Third, for safety protocols. To eliminate human error on site, we recommend a mandatory night shift supervisor sign off before the crew can begin any dismantle operation on the structural form. So to conclude our presentation today, let's wrap up the core takeaway of this entire problem-based learning assignment. As highlighted on the slide, mathematical modeling through ordinary differential equation is not just a theoretical exercise. It provides civil engineers with the precise data-driven boundaries required to balance structured execution and long-term planning. By mastering this ODE framework, we can confidently ensure both urban utility sustainability for our smart cities and structural excellence for heavy infrastructure projects like our bridge pier. So that's all from us. Thank you.